Hey everybody, this is going to be chapter 3, part 2. So in this one, we're going to be talking about dispersion. Some words that you might have heard before, maybe something like variance or standard deviation. These are the things we're going to be talking about in this video. So the first one, the most basic one, is the range. So what this does is you take the maximum value and you take the minimum value and you find that's where your data, that's how wide your data is. That's the range of the data. Now, this is helpful, but it's really susceptible to outliers. So for example, in that Michael Jordan in the Michael Jordan case in UNC, you have one guy making $30 million a year and everybody else making, suppose, $50,000 a year, right? Well, this is not really comparable because that means the range is, suppose there's one person who's unemployed, doesn't have any salary. It means the range is $30 million. So as a prospective student, you might say, wow, that variance is huge. Like the uncertainty there is so large. If I go to UNC and I'm a geology major, geography major, whatever, I don't know what I'm going to graduate with and start making money. That doesn't make sense, right? It's way too variable. But rather, so in this case, range is not a very good number or statistic to tell you about the variability of the data. So the next statistic is called variance. And let's just all stare at the equation for a second, breathe, and let's break it down. So if you remember, we have x, right? Let's start with this x. This x is should be very familiar to you. This x is just all of the data, right? So you have ages, you have income, you have what have you, right? And what you're going to do is for each one of these x's, right? This is what the formula is saying. For each one of these x's, I want to subtract mu, the population mean, right? So if I take all the students in the class and I say, what's your height, right, in inches, and everyone's telling me how tall they are, and I take the average. Okay, I've saved that average. Suppose that average is, I don't know, everyone on average is 5 feet tall, so that's 60 inches. Okay, well, what I'm going to do now is I'm going to take each person's height and subtract off their the average. So some person is 55 inches tall, so they're 5'5", minus 60 inches, they're going to be 5 above the average. Someone else is going to be maybe 45 inches tall, and I subtract 50, and then I have 45. So then I have -5, right? So if I wanted to take an average of the variability of these data, maybe what I want to do is just take the average of those numbers, right? I just want to take the mean difference from the mean. Well, if you remember, the sum of the differences from the mean equals 0. So if I were to do this, let's pretend we have that 1, 2, 3 data set again, right? So the average difference is going to be, or if I subtract the average from each one of 1, 2, and 3, I will have -1, 0, and 1, right? Taking the average of this, it's going to be the sum. It's going to be 0 divided by 3 is going to be 0. So the average difference is 0. That's not true, right? There is some sort of variability in the data. So rather, what we have to do is we have to square each difference. So each time you take the difference, and let's keep going with the 1, 2, 3 example, we need to square that difference. So 1 minus 2, 2 is the average, -1 squared. So that's going to be 1. 2 minus 2 squared is 0, because 2 minus 2 is 0, squared is 0. 3 minus 2 is 1, squared is still 1. So now we have 1, 0, and 1. Take the average of this, we get 2 over 3. So the variance is now 2/3. So that's how you calculate the population variance. So for each observation, you subtract off the average, square that quantity, add them all up, and divide by n. So it's very algorithmic, meaning it's very step by step. So for example, just to kind of go over it, let's do it with this data set. So I'm going to delete all this business. And right here, I'm gonna calculate the mean, right? Or maybe I'll calculate the mean here, right? So I can actually just use a function called average, and I'm just going to use this for the entire thing. Okay, so now I have the average next to each value. I'm gonna keep the formula next to us so we can have a look at it. So the formula says to take x minus mu. So that's going to be, this is my x. Maybe I'll even put here, this is my x, this is my mu. My x minus mu is going to be 1 minus this value, right? So you can see I've done A2, which is this guy, minus B2, which is this guy, and I subtracted them. Now I'm going to take this and I'm going to paste it for each one. So now you can see this one is doing these two subtraction, right? These two, this one's doing these two subtraction. So it's tracking, right? It's going down the road and it's subtracting each one. So now the formula says x minus mu squared. So it's going to be x minus mu squared. So now what I'm going to do is I've already done x minus mu. I need to take this and square it. So let me go do that for each one of them. Right. So now these are all of the squared terms. Cool. Now what this sigma says to do, it says to add. So it wants us to add up all of the x minus mu squared. So I want to add these all up, equals the sum of these guys. Okay, 16.88889. And I want to take this number and I want to divide by my n. So I know my n is 9 because I know it's just these guys right here. But just for completeness, I'll do the count. So this is going to be my n. So now my population variance is going to be 1.876543. So let's suppose instead of x, this was actually salary. I don't know, right? The units of this are a little bit unintuitive. So this is actually salary squared. So I give you my variance and I say, oh, the population variance of these data, this sigma squared, right? That's what this is right here, sigma squared, is $1.87 squared. Okay, well, what does that mean, right? It's a little uninterpretable. We'll get to that in a moment because it's the squared unit. Okay, and remember, we squared everything because if we didn't square things, if you just got rid of this 2 and I hit it, so if I suppose I'm hiding this with my mouse, if I didn't square everything, I would just have x minus mu for each one of these, but we know that that's going to equal 0 every time. So we can't always have no variance, right? There is variability in the data. We know the average is 3.1111, that other data set. So there is some sort of variance, right? And the point of the variance is saying, if I select any random thing, what's the average squared units away from the mean this thing's going to be? So again, a little bit unintuitive. It'll get more clear in a moment when we talk about standard deviation. Okay, sample variance. So if you remember, x bar and mu were calculated the same exact way. The only difference is that the denominator for population mean had a capital N, whereas for sample mean, it had a lowercase n. That's denoting that the capital N is the population size, the lowercase n is the sample size. So sample variance, we're going to use s squared instead of sigma squared. We're going to use x bar instead of mu. and we're going to use little n minus 1 instead of capital N. So if you remember, this one was just capital N by itself. This one is little n minus 1. So the difference, the importance of this is we don't have the full population. So if we do n minus 1, meaning this is going to be slightly smaller than our sample size. If you decrease the denominator, this whole fraction is going to get a little bit larger. So what this is saying is we're actually a little bit less sure because we only have the sample. So this standard deviation, or the sample variance is going to be a little bit larger, just a little bit larger, because we're subtracting 1 off the denominator. Now, if n is like 1,000,000, right, it doesn't really matter if it's 1,000,000 and 1,000,001. But if we're talking about 10 and versus 9, that can actually have a significant impact on how large that sample size is. Now, you might say like, now minus 1 seems so arbitrary, but it's really not. And if you really want to go through the proof of why this is actually correct, quote unquote, then we can talk about it in class. It's a little complicated. Okay, so here's an example. Here's a bunch of data sets, right? Or here's the data set. They subtract off the X bar. This is a sample, so they subtract off X bar. They get all of this. They take the square of each one of these things. Then they add it all up and divide by n minus 1. So if this was, we go back to our example. A moment. Right, and we want to replicate this. We would do everything exactly the same. So instead of calling this mu, we would call this X bar. I'm not going to change it, but it would be called X bar. This would be X minus X bar, or salary minus X bar, X minus X bar squared. So we do the same exact calculation, right? You find mu, in fact, the same exact way. But instead, the only thing that would change is, again, you're still summing. The only thing that would change would be, this would be then minus 1. So 2.11 versus 1.87. So notice how, so maybe I'll just copy this whole thing so we can look at it. So this is population, and this is sample. So again, same number, but I'm going to subtract 1 off of this. So you can see it's actually a little bit different, right? It's about 0.3, 0.2 different, right? So there is some sort of difference in this. And what this is just saying is that, okay, the average, if I just randomly select something, the average number of squared units away from the mean is going to be 1.87 or 2.11. And so on. Okay. So standard deviation. This is sample standard deviation. So if you notice, this is sigma squared, and this is the formula for it, or sorry, S squared. This is the formula for it. And if we go to the standard deviation, it's the same exact formula. It just has this giant square root over it. Because we have S squared, if we just take the square root of both sides, this just becomes S, and this becomes the square root of that whole thing. So effectively, what this is saying to do is it's saying, grab this, let me put it here. This is our units, right? So now what this is saying is just take the square root of this guy. Now we have 1.45. And this is now in units of salary. This is, again, sample. So what this number is saying, if I take any random number, if I randomly select one from this group here, on average, if I do this experiment 1,000 times, if I keep plugging, if I keep pulling, the average distance away from the mean will be 1.45. So if I have an average of 3.1, if I randomly go in there and I grab 2, right? If I grab 2, that difference is going to be 3.11 minus 2. That's going to be 1.11. Oh, it's calculating it over there. It's calculating that over there too. I'll put it here. So 1.11, right? Kind of close to 1.45. If I grab, instead of 2, I grab a 3, that's gonna be very, very small. If I grab a 5, it'll give me negative, right? But we're talking about squaring and then square rooting. So we're talking about absolute value in a way, the absolute difference, the average just distance. But this is what standard deviation is saying. Standard deviation is saying if I randomly select a point out of the data set, on average, it will be 1.45 units, $1.45 away from the average. That's all it's saying. So it's a measure of variability. And further, if the standard deviation is very, very small, it's saying if I randomly pick, so imagine it was 0.05, like 5 cents. That would mean if I randomly select one, on average, that randomly selected point is going to be about 5 cents away from the average. That's not a lot of variability, right? That's right. That's really hovering around that average. There's a lot of data right at that average. Now, if I looked at the Michael Jordan example, the standard deviation of that would be huge. The standard deviation that might be like $10,000. Well, that means that there's a crazy dispersion of data for that sample, right? So that's all standard deviation is trying to really intuitively say. You're just calculating this average difference, average distance rather, from the mean. So here's all the description of those variables again. Here's some major characteristics of standard deviation. It's in the same units as the original data, meaning it's directly interpretable. I have an average of $3.1 and a standard deviation of 1.45. Meaning if I, on average, that thing can be 4.6 or 4.5 or whatever, or it can be 2.6 or 2.4, whatever it is, right? You can kind of say like, oh, that's pretty good, average range there. It is the square root of the average squared distance from the mean. So the squared distance, right? That's what we were calculating before. X minus mu squared, that's the squared distance. We took the average of that, right? Because we took the sigma x minus mu squared divided by n. That's an average. And then we just take the square root of that. That's just all it is. It cannot be negative because it's a distance measured, right? Distances can't be negative. Doesn't make sense. And it's the most widely used measure of dispersion. This is kind of a key point when you report standard deviation. You're not really going to come across like range all that much. Standard deviation is much more applicable. For example, it's like saying people always report averages of things. They don't report the medians. They report the averages. Standard deviation is an average of the differences, right? Okay, so we're going to talk a little bit about the interpretations and uses of standard deviation. So this guy Chebyshev was super famous mathematician. He has this theorem that for any set of observations, sample or population, doesn't matter, the proportion of the values that lie within k standard deviation of the mean is at least 1 minus 1 over k squared, where k is any value greater than 1. So, for example, let's talk about 2 standard deviations, right? So if I have that 3, I'm gonna go back. So this is our standard deviation and our average is 3.11. So I'm just gonna call this 3.11 and 1.45. So this is our mean, and this is our standard deviation. All right, so our 2 standard deviations to the left, meaning subtracting 2 standard deviations, is gonna be 3.11 minus 2 times 1.45. Oops. That's going to be almost 0, about 0.21. And if we replicate this, but instead we're going to do plus, that's going to be about 6. So between 2 standard deviations, Chebyshev is going to say that at least 1 minus 1 over k squared observations lie within that range. So in other words, what he's saying is equals 1 minus 2 squared, right? So 4 really. So he's saying that at least 75% of observations are within 2 standard deviations. At least 75. Could be more, could be all of the data. For example, all of our data is within 2 standard deviations, right? But Chebyshev is saying that you can have some sort of crazy funky distribution. At least 75% will be for sure within 2 standard deviations. So if we said 3 standard deviations, we would square it. So 1 minus 1/9, so 8/9. So at least 88% of observations are within 3 standard deviations. So 3 standard deviations is a pretty wide measure, right? If you're outside of 3 standard deviations, you're pretty much like a random like 12%. That's a pretty low percentage. But that's all this is saying, is just saying that 3 standard deviations effectively is pretty good. Now, the empirical rule is a little bit more particular. Chebyshev was saying for any distribution, any crazy, funky looking crazy thing, right? You can do whatever you want to it. At least that percent will be within k standard deviations. The empirical rule is saying that if you give me a distribution that is both symmetrical and bell-shaped, so a bell curve, a normal distribution, we call them. We'll talk about this later. 68% of the observations lie within 1 standard deviation of the mean, and 95% of the observations lie within 2 standard deviations. So remember, Chebyshev said 75 for 2. The empirical rule says 95% for 2. And then Chebyshev says 88.9% or 89% of observations within 3 standard deviations. The empirical rule says if you give me a bell-shaped symmetrical curve, 99.7% of observations will be within 3 standard deviations. So this is even more strict, even bigger of a claim, saying that almost all the data will be within 3 standard deviations. Now, there are a lot of data that are bell-shaped and symmetrical, but not all. Chebyshev is a much more conservative thing, right? He's not as aggressive. He's saying only 75%, whereas they're saying 95. He's saying 89, where they're saying 99.7. So you can really trust Chebyshev. Trust this a little less, but this is what a lot of things that we're going to be using is going to rely on this bell shape. And the reason why we can do this is because of the central limit theorem, which we'll talk about later. And this is like the foundation of statistics. So I have this thing here. If you have any questions about anything, you'd like me to go over it, you can just put some responses here. I can make this even anonymous, but you know, and so on. But that's all I have for this. Hopefully this is a little bit intuitive, or I was able to breathe a little bit of intuition into this, but I understand if we have to keep, you know, going over this in person, but that will happen at a later time. So I'm going to end recording here. Please email me if you have any questions.